Okay, guys, today we're going to look at implicit differentiation. Um, and essentially, this is a tool we use in order to try and find the derivative when, often when the original equation we're looking at isn't a function. So you can imagine, I have a circle here on the front of the slide, trying to figure out a tangent to that circle. We would have to use the equation of a circle. Well, the equation of a circle is x squared plus y squared equals r squared, right? So then trying to differentiate that is a little bit trickier because of that y squared that's involved. So that's what we're going to take a look at. And there's this one, at first, little confusing aspect of it. And once you grasp that, the rest of it is super, super straightforward, okay? Okay, so let's give it a try. So here's the problem. Determine the equation of the tangents to the curve x plus 2 squared plus y minus 4 all squared equals 2 at x equals -3. Now, doing differentiation on this, the way we know to do it, is rather complicated. Some questions are difficult to write in the form y equals f of x. In these cases, we say that there's not an explicit expression for f of x, but rather there's an implicit relation between x and y. Such curves usually do not represent functions like a circle, okay? We're gonna do a lot of conics here. So I'll just show you some equations of conics and what they might look like. So examples would be x plus 2 squared plus y minus 4 all squared equals 2. That would be the equation of a circle. That would actually be the equation of a circle with its center at -2, 4 and a radius of √2, just in case you want to know. An ellipse also has that x squared and the y squared, but the stretch factors on x and y are not the same, and that's what causes it to be an oval shape, an ellipse. An hyperbola is an example would be 4x squared minus 9y squared equals 36. So we're subtracting there. And then a horizontal parabola. So that would be a parabola like what you know a parabola to be, but on its side. So it would look like a C or a backward C. X equals 3y squared minus 2y plus 6. Okay, so these curves also have tangent lines for any point on the curve, and the derivative exists unless the tangent is parallel to the y-axis, okay? So to find the derivative, we'll apply all the rules we know, assuming that y is some function of x, even though the explicit relationship is unknown, okay? So here's what we're going to do. We're going to differentiate both sides of the equation with respect to x, and then we're going to solve for the derivative of x, otherwise known as dy over dx, or otherwise known as the derivative of y. And this usually involves essentially getting all the terms that involve dy over dx to one side, factoring out the dy over dx, and dividing. So essentially, we're just going to take the derivative of all the terms that we see, and then get dy over dx by itself. Much like the approach I did when we were establishing the quotient rule. Remember, we kind of went through the quotient rule proof in a different way, and then we got that big f derivative in the equation, and then we tried to isolate it. Okay, so we'll do kind of a similar process here. Okay, so we are going to determine an expression for the derivative of x squared plus y squared equals 25 with respect to x. Now, we have talked about the fact that when I want to take the derivative of something that involves addition and subtraction of separate terms, we can just take the derivative of each term. So essentially, we're going to do the same thing right here, okay? Except we're going to take the derivative of every term on both sides of the equal sign, okay? So you know that the derivative of x squared is going to be 2x. That one you're going to be comfortable with. And you know that the 25 is going to turn into a 0 because the constant term, the derivative of the constant term ends up being 0, okay? It's the y squared that we're going to have to talk about for a second. That's going to be written down as 2x plus 2y derivative of y equals 0. And now you're asking yourself, well, what the heck? How did y squared become 2y dy over dx. Now, it's actually, this is the one little thing I said that it's going to be confusing for a second, but once you grasp it, the rest of this is very, very straightforward, okay? And what I want you to do is I want you to think about the chain rule for a second. So if I asked you to take the derivative of some composed function, f of g of x, the derivative of f of g of x was the derivative of f of g of x times the derivative of g of x. We always had to take the derivative of the inside function, right? So, for example, the derivative of f of x all squared would be 2 times f of x times the derivative of the inside function, so the derivative of f of x. It's the same thing here. Y squared ends up being 2 times y times the derivative of the inside function. Okay, really, we've been doing this all along. If you think about y equals x to the 4, the derivative of that is actually the 4 comes to the front, the first guy drops a degree, so that's where I'm getting the 4x cubed, and really then you have to take the derivative of the inside function. It's just that in that example, the inside function was just x, and the derivative of x is just 1. And we never ever wrote times 1 there, right? Because we just knew that the derivative of x was 1. But really, you have always been taking the inside function. We just didn't have to write it down, okay? The difference now, if I go back a slide, is now we have to write it down. So the 2 would come to the front, and I'd be left with 2 times y times the derivative of the inside function. That's where that y derivative comes from. We just don't know what the derivative of the inside function is, and so we say it's the derivative of y, okay? All right, so we've always been taking the derivative of the inside function. It's just that previously it's been 1, okay? All right, so back to this question then. We have 2x plus 2y derivative of y equals 0. So now the goal is just to algebraically manipulate this so that we get the derivative of y by itself. So I'm going to have to subtract 2x from both sides and then divide both sides by 2y. And so that will give me the derivative of y is going to be negative x over y. Okay, so this would be the implicit derivation for x squared plus y squared equals 25. All right, so let's try another one. How about 4x squared minus 9y squared equals 36? Okay, the confusing part is over. Now we just have to follow that kind of process. Okay, so again, we're going to take the derivative of each thing. So maybe just to help bring this home once more, let's just talk about this one for a second. The derivative of that would be the 2 comes to the front, so that would be 8x. It drops a degree, and then I take the derivative of the inside function, which is x, and the derivative of the inside function is 1. And so I never ever write that down. But then over here, I end up the 2 comes to the front, so that's negative 18. Y drops a degree, and then I take the derivative of the inside function. Well, what's the derivative of the inside function? I don't know, so I'll just call it the derivative of the inside function. That's where that derivative of y comes from, okay? Hopefully that kind of helps solidify the conversation we just had. And then for 36, the derivative of that is 0, okay? So you should be looking at 8x minus 18y derivative of y equals 0. Now the goal is to get the derivative of y by itself. So I'm going to subtract 18x from both sides, then I'm going to divide both sides, subtract 8x from both sides, and then I'm going to divide both sides by negative 18y. And then when 8 over 18 would reduce to 4 over 9, okay? And then you had 2 negatives, so overall my answer is positive. So the derivative of y is 4x over 9y, okay? And again, the reason this is called implicit differentiation is because the derivative is not just in terms of x, right? There's a y involved as well, okay? All right, determine an expression for the derivative of x equals 3y squared minus 2y plus 1 with respect to x. So again, I just took the derivative of every term I see, okay? So the derivative of x is 1, 3y squared, the 2 comes to the front, so I'll get 6y times the derivative of the inside function, which is dy over dx. And then this guy, the essentially, let me just write this out for you. This is like a 1, right? So the 1 comes to the front. So that's going to give me a negative 2y to the 0, right? And then times the derivative of the inside function. So I don't have y to the 0 there because y to the 0 is just 1. And then the derivative of 1 would be 0. Okay? I'm going to just quickly hide myself for a second, just in case you can't see where I circled there. Okay, so I was just talking about this negative 2y to the 1, that 1 coming to the front, and then that would be y to the 0, and that's why I didn't mention it. Okay? All right, I'll put myself back. And now I need to get dy over dx by itself. Well, in order to do that, this time I have 2 terms that involve dy over dx, okay? But they're both on the same side. So what I'm going to do is I'm just going to factor dy over dx out, and that's going to leave me with 6y minus 2. And then I just have to divide both sides by 6y minus 2. So dy over dx equals 1 over 6y minus 2. Okay? Awesome. Okay. Determine the slope of the tangent to the curve 2x to the 5 plus x to the 4y plus y to the 5 equals 36 at the point 1, 2. Okay, now this one is just a little bit more loaded. Just a few more steps involved, that's all. And I actually want to, so I want to figure out the equation like I always do, right? I want to figure out the equation of the derivative. But then the added part to this is then I want to know the slope at the point 1, 2. So once I figure out my equation, my derivative, I'm going to plug 1 in for x, 2 in for y, and actually figure out what number that comes to, okay? But the other kind of added layer to this guy happens when we go to take the derivative. The derivative is going to be just a little bit messier. Okay, so what I need you to see here is the derivative of this guy. Well, the 5 will come to the front. Okay, so that'll be 10x to the 4. Then I need you to see the derivative of this guy involves the product rule. Okay, so this is f times g, so I'll have to go with the derivative of f times g plus f times the derivative of g. Okay, so that's going to be the derivative of f. Well, I'm just going to write that out with you right now. That's going to be 4x to the 3, right? Times g plus the derivative of, or sorry, plus f, so x to the 4 times g, which is the derivative of y. Okay, so that's just this guy. So at the front, I would have 10x to the 4, okay, plus, now I took that guy, and then I'm just going to color code all of this for you for a second. So then that guy would be 5y to the 4 derivative of y, right? And then this guy, no, I'm sorry, I needed a different color. Okay, and then this guy would be equals 0. Okay? So I'm going to clear the ink and bring that up to you here. But that is exactly what I just said, right? So I've got 10x to the 4, and then I've got the derivative of f times g plus f times the derivative of g for the product rule. Okay, so just this guy is all of this guy. And then 5y to the 4, derivative of y, and then equals 0. Okay, so now I need to start cleaning this up. Well, again, I have 2 terms that involve the derivative of y. I've got this guy and I've got this guy. Okay, so I need to bring them on one side of the equal sign so I can factor it out. So everything that doesn't involve the derivative of y, I want to factor out, or I want to get rid of. So I'm going to bring those guys over to this side. Okay, so that would look like this. Okay, all I've done is I've moved my 10x to the 4 over, and I've moved my 4x cubed y over to the other side. So now I've got the terms that involve the derivative of y on the left side. I'm going to factor out the derivative of y. Okay, and then I just essentially have to divide by x to the 4 plus y, 5y to the 4. Okay, so if I do that division, this ends up being the implicit differentiation. Okay, now I have been told I want to know the slope. So this equation, again, I just want you to think about this for a sec, because this is what the derivative does. This equation represents the slope of every tangent line I can form at any given point along my circle or my ellipse or my hyperbola, whatever it is, okay? So for this guy, I'm now going to plug 1 in for x, 2 in for y, and actually get the physical slope at that point, okay? So I plugged 1 in for x, 2 in for y, and then I just solve, okay? Take note of my writing here. I'm now saying it's the derivative of y when x is 1 and y is 2, okay? All right, and so that becomes, when I do that, negative 2 over 9. So the slope of the tangent line for this equation here at the point 1 comma 2, I would have a slope for that tangent line of negative 2 over 9. Okay? Awesome. Okay, so that is your homework. And next we're going to talk about higher derivatives. Okay, so taking the second derivative, taking the third derivative. So I will see you there when you choose to see me. Okay, take care, guys.